Hello, today we'll continue our introduction. So let's take a look at the type of structures or classification of structures that we will be talking about in structural analysis. So the most structures will fall into one of these structures. So the first type of structure that we will discuss is beams. The other ones are trusses and rigid frames. So here we will see what type of structures are beams. We call them as beams. What type of structure we call them as trusses. So by definition, let's draw a beam here. In order for us to call this structure as a beam, it should be under transverse loading only. Meaning that this loading can only create bending deformations. And in order to have that, these structures have to subject it to transverse loading only, no axial loading. So in order to analyze such beam structures, we have to consider only bending deformations, no axial deformations, okay? So we just say that it will deform like that under the given loading. So basically, in order for us to call a structure as beam, it should undergo bending deformation only. So the trusses, let's again draw a very simple truss structure here. We do draw it this way. The main property of a truss, it will undergo only axial deformation. So the members of the truss, they don't bend, they just elongate or shorten. That's the main property. And in order to satisfy that, all the loadings must be applied to the nodes, to the joints. So basically, a truss structure is a structure that resists the applied loading by axial deformations. When we have a beam deformation only, it's a beam for us. Axial deformation only, it's a truss for us. Now, when we have a frame structure on the other hand, so let's draw a simple frame. Let's put some loading here. It's the combination of beam and truss actually in terms of deformation. So it undergoes both bending and axial deformation. So as you see in structural analysis, we classify the structures according to their deformation behavior. So we have beams undergo bending deformation, truss undergo axial deformation, frame undergoes bending and axial deformation. So this is the classification that we make. Now here we call them, we just don't call them frames, but we have the rigid here. The reason of defining rigid is as follows. The members are not rigid, but the joints are rigid. So let me draw another frame here. So let's say that these angles at the joints are equal to 90 degrees. So this is the undeformed shape. Let's say that I apply this loading, I push the structure from its sides, and then it starts to deform. So as it deforms, the members change their shape, they deform, but the joints, they don't deform. If initially they are 90 degrees, in the deformed state, they are still 90 degrees. So that's why we call them rigid frames. So by definition, this is another simplification that we make in the structural analysis. We say that the joints are rigid. The angles at the joints do not change as the structure deforms. So we have in structural analysis, as a beginning, we have three types of structures: beams, trusses, and rigid frames, and the classification here is based on the deformation types. Now, we talked about it, but let's go over it one more time. Statically, determinate, and indeterminate structures. How can we define a determinate structure, indeterminate structure? Let's take a look at that. So I'll use the same classification. On one side, I have statically, determinate beam. Versus statically indeterminate beam. The statically determinate beam is the simplest beam that we can have, right? We have a simply supported beam, let's say here. And it undergoes subject to certain loadings. Here, remember that that's a beam, so I'm interested in only the bending deformation. So unknown support reactions for me is this one, R1, and the unknown support reaction is, here is R2. I don't really worry about the horizontal component of the support reaction at point A, because really I'm not interested in the axial deformations or the axial forces on this member. Now, here there's a reason of saying statically, because it means that we are looking at the forces, okay? Can we determine all the forces by using the equilibrium equations or not? That's the question that we are asking. So, how many unknowns do we have? We have two unknowns, which is R1 and R2, two vertical support reactions. These are the reactions related to the bending deformation. And I can write two equilibrium equations. Since I call this as a beam, I don't have to worry about the equilibrium in the horizontal direction, because by definition I know that there is no loading in the axial direction, in the horizontal direction. All the loadings should be in the transverse direction. So my first equilibrium equation, sum of forces in y direction is equal to 0, or sum of moments anywhere in this structure. You can just check it at point A, at point B, doesn't matter. That's equal to 0. So as you see, we got two unknowns. I can write two equilibrium equations. I can determine all the unknown forces by using the equilibrium equations. So that's a determinate structure. So let's work on another example. So let's say I have let's put a hinge here, internal hinge. Point A, B, CD, and here I have an internal hinge. So what is the main property of internal hinge? It means that at point A, the moment must be equal to 0. Okay, it's not the sum of moment. At point A, B, the moment must be equal to 0. So again, let's take a look at the unknowns. So the unknown for me at point A will be R1. Since I define this as a beam, I know that the horizontal component of the reaction force is equal to 0. There's no loading on it. R2 and R3. So we have three unknowns. Three unknown support reactions, which is R1, R2, and R3. And this time I can write again three equilibrium equations. Remember that the equilibrium equations are the equations related to the forces. So the first equilibrium equation I can write is sum of forces in Y must be equal to 0. The second equilibrium equation, sum of moments anywhere in the structure is equal to 0. And my third equilibrium equation, the moment at A must be equal to 0. This is the additional equation that we get from the internal hinge. So again, when I look at this structure, that's a determinant structure for me, because I can determine all the unknown forces by just using the equilibrium equations. Now let's put, for completeness, an indeterminate structure here. So let's say that I have the following support conditions under certain loading. Remember that the loads must be in the transverse direction. So how many unknowns do I have? Let's say that this is point A, point B. I don't know what the moment at A is. I also don't know what the vertical reaction at A is. Likewise, I don't know what the vertical reaction at B. Let me repeat one more time. That's a beam. I'm not worried about the axial deformations. And by definition, all the applied loading must be in the transverse direction. So the horizontal component at point A of the reactions at A and B, they are equal to 0, or I'm not really interested. So how many unknowns do we have? We have three unknowns. MA, RA, and RB. How many equilibrium equations I can write? I can only write two equilibrium equations, which is sum of forces in Y must be equal to 0. Sum of moments must be equal to 0. So as you see, three unknowns, two equilibrium equations. So degree of indeterminacy is 1. So I need one additional equation to analyze that structure. Or there's another wording. And the structure has one redundant support reaction. So why do we say redundant? Because in order to satisfy the equilibrium condition, we don't need three resistances. All I need is two. If I have two support reactions, RA and RB, I can satisfy the equilibrium. But I added a redundant support condition, MA, to make the structure a little bit more safer. Why? I mean, remember that these are all actual structures. These are the mathematical representations of actual structures. For any reason, one of the supports fail. Let's say that this support failed. It's gone. A car hit, a truck hit, and then it's gone. Do I see a collapse of the structure? The answer is no. Why? Because I still have sufficient resistance here, MA and RA, to keep the structure stable, to satisfy the equilibrium condition. But in the determined structure case, if I lose the support at point B, then I can only have the vertical resistance at A, and because of this reason, this structure will collapse. How does it collapse? If we lose B, it will rotate here. I see a huge rotation. There is nothing else to avoid that rotation, and I end up with the collapse of the structure. So determinant structures do not have any redundancy. They just have the sufficient condition to satisfy the equilibrium. But when we take a look at the indeterminate structure, we have redundancies in it. So if something happens, if due to any reason you end up with a failure of one of the support conditions, then you still have a stable structure. Maybe you see damage, but you don't lose the equilibrium and you don't see any collapse. So this is the behavior point of view, but in terms of analysis, this is important for us. 1 degree of indeterminacy is equal to 1, which tells us I need one additional equation. So that's the story in the beams. Now let's take a look at the trusses now. We will do it very briefly because we are more interested in the determinants in terms of deformations, but just for completeness, let's take a look at the determinate trusses. Versus indeterminate trusses. So in order to do that, I'll just draw a couple of trusses and we will discuss whether these are determinate or indeterminate. So that's our first truss. Let me put this one here. This is the second truss that we can have. And let me draw one more truss here. So the question here is this a determinate truss or indeterminate truss? The first one, second one, and third one. So let's analyze them, okay? So in order to do the analysis, so I'll just start with the support reactions. R1, R2, and R3. These are the support reactions of for the first structure. For the second one, and the third one. So the first question that we are going to ask is, can we determine all the support reactions by using the equilibrium equations? So in the first case, I got two unknown reactions. I can write three equilibrium equations In the second one, I got 4 unknown reactions. And in the third one, I got 3 unknown reactions. And for every one of them, I can write 3 equilibrium equations. There is no difference in that. This is a 2D truss system, and I can only write 3 equilibrium equations. So once we examine these 3, we say that this is determinate, the second one is indeterminate, and the third one is again determinate. So by using the equilibrium equations, I can actually determine or cannot determine the support reactions. So we call this external indeterminacy. So by using the support reactions, I can actually, by using the equilibrium equations, I can determine the support reactions or not. But the second question is, okay, I know the support reactions. Can I calculate the member end forces or the axial forces on each truss member? Now, for this, if you remember, if you go back to your static courses, we can go node by node, right? Or joint by joint. And at every joint, we can write 2 equilibrium equations. So at each joint, we can write 2 equilibrium equations, which are sum of forces in X must be equal to 0 and sum of forces in Y must be equal to 0. Okay, by using these equilibrium equations, can I determine the unknown member forces? Let's take a look at it. So, how many member forces do I have? In the first structure, I have 5 member forces. I got 5 members, right? For each member, I have an unknown axial load. Plus, I got 3 support reactions. So, for this case, I have a total of 8 unknowns. How many equilibrium equations can I write to determine the truss forces? I got 1, 2, 3, 4 joints. And I can write 2 equilibrium equation at each joint. So basically, I end up with 8 equilibrium equation. So in this first truss, I got 8 unknowns, 8 equilibrium equations. Again, that's a determinate structure for me. So I can determine also the truss forces. Now, let's take a look at the third structure right now. In the third structure, I got 6 members. And 3 support reactions. So the number of unknowns for me is 9. I got 9 unknowns. How many equilibrium equations I can write? Again, I got 4 nodes, or 4 joints, sorry. 4 joints will give me 8 equilibrium equations. So the result is that's an indeterminate. So in the third truss structure, even though I can determine the support reactions by using the equilibrium equations, I cannot calculate all the truss forces because I'm missing one equilibrium equation. So this is an indeterminate structure, but the type of indeterminacy is an internally indeterminate structure. Even though I can calculate the support reactions, I cannot calculate all the membrane forces. In the second case, if I knew the support reactions, I can actually determine all the membrane forces. So if we just write different classifications for these type of trusses, so the first one, internally and externally determinate structure. Now the second structure is externally indeterminate but it's internally determinate structure. Because if I know the support reactions, if I can calculate the support reactions by some other methods, I can determine all the truss forces by using the equilibrium equation. So for me, it's an internally determinate structure. And the third one is externally determinate but it is internally indeterminate structure. Okay, so why are we doing all this? It's just to understand the behavior, okay? And to try to decide what type of analysis method that we want to use, how we are going to use these type of structures. Of course, we are looking at the static determinants, so everything is related with the forces. Can we calculate the forces, internal forces? Can I calculate the support reactions and so on? So all these terms are related to the forces within the members. Okay, so I mean these are some terms, but since in this class we will be using the displacement-based analysis methods, actually the structure, if a structure is statically determined or indeterminate, it won't matter for us. We will apply the same procedure to the statically determined and indeterminate structures. Now, I can do the same thing for the frames, but there's nothing special for it. And internal determinacy of frame structures is a little bit complicated, so we really don't focus on that. What is important for us is actually is not the static determinacy, but it is the kinematic determinacy or indeterminacy. This is what we care. Because the solution methods, the analysis methods that we will focus is related to the deformation of the structure. So here, the term kinematic refers to the deformation, not the forces, but the deformation of the structure. Now, let me write the definition and then we will continue to discuss. So, kinematic indeterminacy refers to the number displacement quantities that are necessary to define deformational response of a structure. So what does it mean? So let's take a fixed beam. And I have another beam here. This end is fixed. And I have a pin support here. Okay? Let's say that that's point A. That's point B. And they are both under uniformly distributed load. Now, for us, the first one is a kinematically determinate structure. Why kinematic determinate structures? Because we know all displacement values at point A and B. If I know all the displacement values at these ends of these two members at points A and B, by using the integration or any other method, I can determine the deformed shape of the structure under this given loading. Okay, so that's why that structure is a kinematically determinate structure. I know all the values of all the boundary conditions. By using the differential equation for bending, I can determine all the deformed shape of the structure. So this is a kinematically determinate. So what we are interested in kinematic determinants is the displacement values at the boundaries. In that case, delta y is equal to 0, rotation at A is equal to 0. This is at A also. So delta y at B is equal to 0. Rotation at B is equal to 0. So these are the boundary conditions. And I have four known boundary conditions. And this will help me to analyze a fourth order differential equation. Now when we look at the second beam, if we try to sketch the deformed shape, again let's call this point A and B. Here there's one unknown. I don't know what theta B is. So because of this reason, this is a kinematically indeterminate structure. Why? Because I don't know the value of theta B. I know delta y at A is equal to 0. I know that rotation at A is equal to 0. Delta YB is equal to 0, but I don't know what theta B is. So I'm missing one of the boundary condition. So this is first degree kinematically indeterminate structure. So how do we use it? That's what we are going to learn in the structural analysis course. So in the structural analysis course, let me repeat one more time. We will be focusing on displacement-based analysis methods. And since we are interested in the displacements or the deformations of the structure, We are actually interested in what we don't know in displacements. We are not really worried about the static determinacy or indeterminacy of a structure, but mainly we are worried about kinematic indeterminacy or determinacy of a structure. And here, since this is a first degree kinematically indeterminate structure, I have to find another equation and combine it with the equations that I'm working with to analyze such a structure. Of course, here we determine the kinematic determinacy or indeterminacy of a single member, a single beam. Now, what will happen if I have a more complicated structure? How can I determine the degree of kinematic indeterminacy or the number of unknowns that I have to calculate in a structure? This is what we are going to discuss in the next class.